Welcome back. So today we are going to be doing lecture number 19, which is about fluids. So what are fluids? Well, fluids are basically anything that can flow. Water, for example, alcohol, oil, they can flow, but there are other things that can flow that you might not think about as being fluids, like ice in a glacier. A glacier can flow, so over a long extended period of time we see that ice is like a fluid. Gases are also fluids. Air can flow, so air is also a fluid. So we'll be talking about any of these kind of quantities, any of these type of materials that can flow. Now, for most of the semester, for most of 1111, we've been talking about very, very simple types of systems like point particles and things like that. We looked at somewhat more complicated systems when we looked at rotational motion, things that can rotate. Well, we're going to be looking at a very different kind of material, very different kind of system, fluids, for this lecture. So it's going to turn out that a very important characteristic of a fluid is the density. Now, there are many different kinds of densities. There can be a charge density, an energy density, something like that. We can have a density in terms of, say, the density of something per a linear length, or an area, or a volume. When we talk about density here, we're actually talking about a mass volume density, the mass per volume. But we'll typically just for now refer to it just as the density. But keep in mind, it's really only one kind of density. So we'll define the density as the mass of an object divided by its volume. The symbol that we'll use for density is a lowercase Greek letter rho. So that's a lowercase Greek rho. So what are the units of rho going to be? What are the units of density, or what are the standard SI units? Well, standard SI unit for mass is kilogram. Standard SI unit for volume, meters cubed. So the standard SI unit for density will be kilogram per meter cubed. Now let's look at an example. Here I've got a little cube of brass. Let's see if we can figure out what the density is. So let's imagine we've got this cube. And this cube, I measured the sides, and they were, let's say, 3.15 centimeters on a side. Length, width, and height. And I measured the mass, and the mass turned out to be 265.0 grams. Let's figure out what's the density of this thing, and let's put the density in terms of standard SI units. So the density will be the mass. In kilograms, that would be 0.2650 kilograms. Divided by the volume. The volume of a cube is length times width times height, or 3.15 centimeters cubed, or 0.0315 meters cubed. Divide that out, and we get a value of 8,480 kilograms per cubic meter. There we go. All right, very, very good. So that's basically how you determine the density of something. You take its mass divided by a volume. Now, let's just think about that for a second. 8,480, that's a very big number. How does such a small object have such a large density? Well, the density is basically just dependent on the material that the object is made of, not the size of the object or just the mass of the object. So even though this is a small object, it has a small mass and a small volume. The density is basically the same density that anything that's brass is made of. Now, that's a little not exactly true, because there are different types of brass, different amounts of the alloys, of the materials that make up the alloy. So brass can actually have a different range of values. But any type of brass that is made of this particular alloy of brass would have the same density. Something that was twice as big would have twice the volume, but also twice the mass. So the ratio would be the same. what this is basically telling us is that for this type of brass, if we had a sample that was 1 cubic meter. Now, how much is 1 cubic meter? That would be 1 meter by 1 meter by 1 meter. That would be a huge piece of brass. If we had that much brass, it would have a mass of 8,480 kilograms. So that's why this number is so big, because we're talking about what's the mass of 1 cubic meter of that substance. Okay? So even though you might have a small particular sample, that can have a large value. Or you could have a large object with a small density. It really doesn't matter. What it's basically telling you is a property of that particular material itself. Now, a related quantity to density is called the specific gravity. I'll just write it as SG. The specific gravity is the density of the object divided by the density of water. So the specific gravity is just rho of whatever our object is divided by the density of water. Now, the density of water is something that we're going to be using a lot, so this is a quantity that I do expect you to remember. The density of water is 1,000. 1,000 kilograms per cubic meter. To 3 sig figs, 1.00 times 10 to the 3 kilograms per cubic meter. You can just think of it as 1,000, but remember that 1,000 is accurate to 3 sig figs. So let's figure out what's the specific gravity of brass. Well, that would be, what did we find? 8,480 kilograms per cubic meter divided by 1,000. Now, what happens to the units? Well, notice we've got kilograms per cubic meter in the numerator, kilograms per cubic meter in the denominator. They cancel out. 8,480 divided by 1,000 is 8.48. So the specific gravity of brass is 8.48, or for this particular sample of brass. Now, what does that mean? That tells us that this particular type of brass is 8.48 times as dense as water. It is more dense than water. It is 8.48 times as dense as water. If you had equal volumes of this brass and water, the sample of the brass would be 8.48 times as massive as the water, 8.48 times as heavy as the water, the weight, etc., etc. Okay, so that's what specific gravity tells us. It basically tells us how the density compares to the density of water. Now, one thing about fluids is, how do forces work on fluids? We've talked about applying forces to objects and making them accelerate. Do fluids respond in the same way? Well, not exactly. Let me get a fluid and I'll be right back. So, when we try to apply a force on a fluid, like if I were going to apply a force on this mass and cause it to accelerate, if I try to push on this fluid, the fluid just moves around and kind of surrounds my finger. It doesn't accelerate the way a solid mass does. So we need to discuss forces in a different way when we're talking about fluids. Let's imagine we have a sample of a fluid with some object submerged in the fluid. That fluid applies forces on the object, but it does so from all sorts of different directions. It pushes on it from the left, pushing to the right. It pushes on it to the left, it pushes on it from above, pushing down, it pushes on it from below up, it pushes on it from the front, it pushes on it from the back, it pushes on it in all sorts of different directions. The quantity that's actually going to be very useful when talking about fluids is called the pressure. Now, the symbol that we'll use for pressure is a capital letter P. Now, do not confuse P for pressure with what? P for Well, momentum, P for power. So don't confuse P for pressure with any of those other P's. Hopefully from context it will always be obvious what we're talking about. The pressure we will define as the force divided by an area. So let's imagine we take, say, one section of this object. So let's say here's the front face of the object. And we look at what force the fluid is exerting on this front face. So how much force is that fluid pushing on the face? The pressure will be whatever that force is acting over that area divided by the area. The units of pressure will then be the units of force, so the standard SI unit would be a Newton, divided by the units of area. The standard SI unit for an area would be meters squared, so the standard SI unit for pressure is a Newton per meter squared. Now that combination of units is something we're going to be using often enough that it's got its own name. 1 Newton per meter squared is called a Pascal. And we will write that as a capital P lowercase a. So at least that won't be confused with P for pressure or any of the other P's. So that'll be our standard SI unit for pressure, a Pascal, which is 1 Newton per meter squared. There are other units, and probably some units that you might be familiar with. For example, if you have ever put air into a car tire, so if you have a car tire and you are filling it up with air and you've got a nozzle here and you fill it up with air, you might fill that up to some pressure, maybe 45 PSI. Well, what is a PSI? PSI stands for pound per square inch. And that's just another unit of pressure. Notice, pound is another unit of force. Inch squared, that's another unit of area. So a pound per square inch, that is a pressure being applied over an area. So what this means is, if you've got a pressure of 45 psi in your tire, inside that tire, the air is pushing out on the inside of that tire with a force of 45 pounds for every square inch. Now, actually that's not exactly right, because it's actually pushing more than that, because the air on the outside is pushing inward also. There is another pressure that we have to deal with, and we're dealing with it all the time. Well, most of the time, and that is the pressure from the atmosphere. We are actually in a fluid right now, and that fluid is the air of our atmosphere, and that is pushing on us all the time. That pressure is called atmospheric pressure. And the amount that it's pushing on us is sometimes referred to as 1 atmosphere, 1 ATM. So 1 ATM stands for 1 standard atmospheric pressure. It's kind of the average pressure that the Earth's atmosphere is pushing on us down here at sea level. It has a value of 1.013 times 10 to the 5th pascals. So, back to the tire. If your tire was completely deflated with no pressure, no extra pressure pushing out, then you'd have 1 atmosphere of pressure on the outside of the tire. Imagine you take the entire hubcap out, not the hubcap, but the wheel rim. Take that completely out, so you just have the rubber tire. Well, you'd have 1 atmosphere of pressure on the inside pushing in on the tire, but 1 atmosphere on the outside pushing out. You'd have equal pressures pushing in and out. This 45 psi, that pressure is actually above the atmospheric pressure. So that extra pressure is what the 45 psi means. It's actually above and beyond, so to speak, the atmospheric pressure. Okay, so that's what that means. Very, very good. Now, let's imagine being in another fluid, like we were just talking about here, rather than just atmospheric pressure, let's imagine that we are in another fluid like water or some other kind of liquid. Let's take a look at what happens in that case. If you've ever been swimming in a body of water like a lake or an ocean or something like that, or a swimming pool, you've probably noticed that as you get deeper in the water, you feel the pressure of that water pushing on you. Well, let's see if we can figure out just how that pressure increases. How, as you go below the surface, the pressure from the water actually pushes more on you. Let's imagine we're looking at a box of water, just this volume of water. There's nothing surrounding it, no real box, but just kind of like a box-shaped volume of water underneath the surface. Let's imagine that it's got a cross-sectional area of A on the top and a height of H. Now, we know that down at the bottom there'll be some pressure of the water. We'll call that P2, and up at the top, some pressure of the water, P1. Now, let's imagine we take this box out and let's look at the forces just acting on this box. We know that there'll be some force acting on the left side and some force acting on the right side, but with everything else being equal, we would expect those forces to be exactly the same, but opposite directions. So we'll assume those cancel each other out. We would expect there to be a force from the front and a force from the back, pushing on it front and back. Again, we would expect those to be equal and cancel out. Now, what about the forces in the vertical direction? Well, we would expect there to be a weight for the water itself. We'll just call that mg, a weight pulling it down. There's the force from the pressure on the top. Now remember, pressure is force per area, so the force would be the pressure times the area. So the force at the top, F1, that would be the pressure at the top, P1, times the area A. So the force at the top would be P1A. The force at the bottom, because the pressure is different, would be P2A. And that would be a pressure pushing up from the water below, pushing upward on the box. Now, yes, the box would push on the water down, but we're looking at the forces on the section of water, not the forces that this water exerts on other water, but what does the surrounding water exert on this box of water, so to speak. So here we have the forces acting on this section. Now, as long as the water is stationary, is not swirling around or anything like that, we would expect that box to be stationary, that volume of water to not be moving. In other words, the net force acting on that water should be zero. So, looking in the y direction, the net forces acting in the y direction would be P2A, that's in the positive direction, minus P1A in the negative direction, minus mg in the negative direction, and all of those should equal zero. Because it's not moving, we expect the net force to be zero. Well, bringing the P1A plus mg over to the other side, we have P2 equals P1 plus mg dividing by A. Sorry, forgot that. Divide by A, we have P2 equals P1 minus, plus mg over A. Okay, there we go. Now, the mass, let's think of the mass is the density times the volume. We know volume is mass per density. So, the density is mass per volume, so the mass will be the volume times the density times the volume, if we assume that we have a uniform density. So we'll make an assumption that the density is a constant. Now for water, that's a pretty good approximation. That the density of water, even if you go down fairly deep in water, the density does not change that much. Water is fairly incompressible. It doesn't compress when you apply forces to it. Not much, okay? Enough for us to assume that it's constant. So we'll say that the mass is the density times the volume. Now what's the volume? Well, the volume of a rectangular box is just going to be the area of the base times the height. In other words, A times H. So this will be rho times the volume is A times H. Dividing by A, we have M equals rho G, and then times, rho H times G, we get mg over A is rho GH. So let's just go over that again. So multiply by G, divide by A, so we divide off the A, multiply by G, we have mg over A equals rho GH. There we go. So mg over A we'll write as rho GH, and we have that P2 is equal to P1 plus rho GH. And there we go. This tells us how the pressure increases as you go down in the fluid. Now what's really going on here? Just imagine, say if you're swimming up here, and then you go down deeper and come down here, you've got all of this water kind of sitting on top of you. You feel that weight. It's very much like if I have this book here, here's a book, and I were to just put my hand under the book, I now feel the weight of the book on top of my hand. Well, in the same way, if you go under the water, you now feel the weight of that water above you. And that's why the pressure is increasing, because the farther you go, the more water you have above you that you're experiencing that weight. You're supporting that much more weight, so the pressure increases. So that's basically where this is coming from. It's the increase in the weight of the fluid above you that's now pushing down on you. So as you go down from some initial pressure P1, you go down a distance h in the fluid of density rho. The pressure down below at P2 will then be the original pressure P1 plus rho GH. All right, great. Let's stick some numbers in here.